Hi, my name is Alexa. I'm a PhD candidate at Cornell, and today I'll be talking about verifying dynamic trait objects in Rust, our contribution for the Software Engineering in Practice track. This is joint work with Daniel and Nathan at AWS and Adrian at Cornell. So to start with, I want to highlight the main ideas that we'll talk about in the paper today. The first is that we'll see how we can model this particular language feature, dynamic trait objects, in a backend verification framework. We'll show that our tool Kani is the first verification-focused tool, to our knowledge, that covers the cases of this language feature that we're most concerned with. Next, we'll look at how we're able to improve the performance of verification of code that uses this feature by applying Rust type information. In one case study, this leads to a 15 times performance improvement. So let's look at a concrete example of what I mean by verifying code that uses dynamic trait objects. It's not important to fully understand this code, but let's look into it. So to start with, we're creating a box closure, which is just a heap allocated closure or anonymous function, and we're naming it f. The din keyword on line 2 indicates that this closure should be dynamically dispatched, and later in the talk we'll talk about what that means. So this closure takes a single argument x and asserts that it's well-formed. Later on line 8, we call the closure. So one question we can ask in terms of verification is, for all possible inputs y, is there some bad execution outcome? Here, that might just mean, is there some input that can cause our well-formedness check to fail, or maybe we're looking at some other dynamic failures later in this code. So in our tool, kani, we can answer this question by replacing the input with a call to kani any, which models a non-deterministic or symbolic input that can be any value of this type. So that's one way to answer the question of, does this code verify? You might ask, okay, din, I don't see this in Rust all the time. Is this really something we need to handle in a verification tool? Our paper has a pretty simple empirical evaluation that found that din trait objects are used explicitly or using the din keyword in 37% of popular crates, and implicitly, often through linking the standard library, in around 70%. So this is a feature of Rust that you need to deal with if you want to handle lots of real-world Rust code. To give some background on kani, kani is a new verifier for Rust based on bit-precise model checking. Our initial focus is on sequential and bounded Rust, and kani is based on the idea of symbolic evaluation. So we're concerned with exploring all possible program paths, as opposed to symbolic execution, which might only focus on some paths. Two important goals to keep in mind here is that kani wants to enable verification on existing projects. So we'd rather not restrict ourselves to a small set of Rust. We want to be able to handle lots of real-world code. In addition, we're aimed at continuous integration in the sense that other teams at Amazon have used a similar tool for C to run proofs in CI, and we'd like to be able to do the same thing for kani. So I have an example of a kani proof on the right. So the idea here is we can create a series of non-deterministic inputs using that kani any function. We constrain inputs to represent valid values, for example, using kani assume. We call the function under verification, and then we check that it meets the specification for this proof by asserting values in Rust syntax. So we can have many asserts that call Rust functions or otherwise use Rust syntax there. Now let's look at what we'll talk about today. So I want to start with talking about the state of the art for related Rust verification projects. I'll give some context behind how the Rust compiler implementation of trait objects works. We'll talk about specifically how to model trait objects in a verification project. We'll look at that performance improvement, and finally, I'll leave you some takeaways. So let's look at the state of the art. So there's been a lot of really exciting and interesting work in formally understanding Rust semantics. I'm highlighting just two of the papers here, Rust Belt and Oxide, which are both about understanding the formal foundations of Rust. Both of these projects do really incredible work, especially in understanding the borrow checker and other similar parts of the Rust language. However, on the subject of traits, these papers kind of defer the project problem to later, saying things like, traits are an orthogonal feature of Rust, akin to Haskell type classes. And again, they're not really seen as an essential part of Rust or a completely novel part of Rust. And while it's true that traits share some similarities to Haskell type classes, today I want to argue that verification tools can and do stumble on these well-understood language features. So if you're concerned with applying software engineering research in verification in practice, you really need to be able to wrangle with these language features that might have surprisingly tricky implementations. To understand the state of the art for Rust verification, we really need to understand standard Rust compilation. So on the left, we take our Rust source code, we go through a series of transformations that I'm not going to focus on today, and it's including a series of intermediate representations, but then we land on Rust MAR, or the mid-level intermediate representation. This is where a lot of the core Rust analysis happens. The Rust compiler later emits LLVM IR, or the shared compiler infrastructure IR, and then LLVM lowers that to machine code. Because Rust is a newer language, a lot of the verification projects focus on moving Rust to existing verification backends or frameworks. Because LLVM predates Rust rather substantially, a lot of projects focus on LLVM IR. So the SMAC project goes to Boogie, which then goes to the Z3 SMT solver, and the Rust verification tools, or RVT project, is based on both CLI and Seahorn as two example backends. One problem here is that when you start at LLVM IR, you lose a lot of Rust-specific context, especially around the type system. In addition, the CLI backend is really focused on bug finding over soundness, so it doesn't do as exhaustive of path exploration as we might want in a verification tool. On the other hand, there are different tools that target the Rust MAR level. For example, the Prosty tool based on the Viper infrastructure, Crux MAR based on Crucible, and our own tool Kani, which is based on the C-bounded model checker, or CBMC. So the advantage here is we get to keep a lot of Rust type information, with a disadvantage that there's a much larger semantic gap between Rust and the backend verification languages. A lot of these languages are based on C, C++, or other languages that, while similar to Rust, have a lot of differences in their type systems. So here we're going to focus on this idea that we start with MAR and we want to translate to Go2C, which is CBMC's C-like representation. And in doing this and examining the semantic gap, we found that one of the most challenging components is handling Rust trait objects. So that's the focus of this paper and what I'll be talking about today. So let's get some context behind how Rust implements trait objects. And to do that, we'll start with traits in general. So quoting from the Rust blog, the trait system is the secret sauce that gives Rust the ergonomic and expressive feel of a high-level language while retaining low-level control. So on the right, we have an example trait called countable. This trait says that objects that implement the trait must implement the function count, which takes a reference to self and returns a usize. So here are two different concrete implementations of count, or the countable trait. So vectors might return their length, and buckets might return their index, by example. Now, when we think about how traits are actually dispatched, or how the methods on the trait object are called, there's two different options. The first is that traits can be statically dispatched. So the idea here that you see in the print count example is we say that print count takes in some object that implements countable, and then we can call a.count on that object. And what the compiler does under the hood here is it generates a separate copy of the abstraction for each concrete instance. More specifically, the Rust compiler will go through a process called monomorphization that stamps out a separate copy of this function for every concrete object that implements it. So here we have different versions of print count for vector and bucket that call their corresponding methods. However, there might be times where the user really doesn't want to have to statically stamp out all these different versions, maybe for trading off code size, or they have some reason that they don't want to specify at compile time what the concrete type will be. Instead, the user can opt into dynamic dispatch. So this allows there to be an indirection where the type is not known at compile time. So dynamic dispatch is invoked via this din keyword. So here we have a version of print count that maybe wants to branch on some user input, as you can see in lines 11 and 12, where we don't actually know at compile time what concrete type will be passed. Now the question is, given this print count implementation, how do we concretely know what function to call for count? So where does the code actually jump to when it hits this count if you don't know at runtime what the type of A is? And the answer that Rust uses is based on a lot of previous languages, or similar to a lot of previous languages, and it's called virtual method tables, or vtables. And the idea is that at compile time, we'll build an object that maps important metadata for each object, and then that's passed around dynamically at runtime. So for the Rust compiler, vtables consists of some important metadata like the size and alignment of the object, as well as the address of drop, which is the destructor in Rust, and then the address of any trait-defined functions, like our count example. So when we actually think about the type of A, or the dynamic trait object, A is a fat pointer, which in Rust is just a double wide pointer. So the first pointer will be the address of the data itself, so that either the vector or the bucket, and the second pointer will be the address of the vtable, so either of the two vtables shown on the right, chosen dynamically at runtime. Now when we have a call to a.count, like in the print example, we essentially replace a.count, and I'm using a sort of pseudocode here because this happens at the MAR level instead of at the Rust surface level. But the idea is that we replace this call to a.count by looking up a's vtable and the count method, and then passing in as self, which is what the a dot is doing, a reference to a data, which will be a pointer to the actual object. So that was a whirlwind tour of trait objects in Rust. Now I want to talk specifically about how we model these in a verification tool. So for kani, our idea is that we want to essentially compile from MAR to a C-like representation. And there are 2 points where we need to most concretely reason about dynamic trait objects. The first is at object creation. So this is when we are actually taking some concrete object, casting it as a dynamic trait object, and essentially erasing its type. The second is at dynamic object lookup, where we have some variable or object of a dynamic trait object type, and we want to call a trait-defined method like count on it. So here we're going to follow the example of the Rust compiler and generate a C-like name structure representing the vtable. And we'll construct a new vtable for every concrete type and trait type pair, because this can be shared across objects of those same 2 types. So we add in the Rust compiler metadata, and then for count, we add in the actual address of the count method we're concerned with. So I have a note here that while it looks like we're using the name count, it's actually a little more complicated than that because of Rust, trait inheritance, and generics. And you can see our paper for more details on that. Now to replace the dynamic object lookup, we'll again access the vtables method as well as the data pointer. So that's the rough idea of implementing dynamic trait objects in a verification backend. But even though that might have seemed relatively simple, there's actually a lot of complicated interactions that happen with other language features. So for example, there are auto or marker traits in Rust that don't have associated methods. You can have box trait objects or heat-up allocated trait objects. And as we saw in the intro, you can have box trait closures or anonymous functions. And across these different examples, many of the different tools that we looked at, including previous versions of kani, would fail on at least one of these cases, often with errors that have to do with not knowing sizes at compile time or not being able to handle unsizing of pointers or having unimplemented flavors of cast. So really, there is a lot of difficulty here in implementing this feature, and we hope this paper can help people understand the things kani went through to be able to handle as much of this feature as possible. So let's look at a specific example of this modeling task. So dynamic closures, as we saw in the example, are when you treat a closure as a dynamically dispatched object. And here specifically, we're using a din fun, where fun is a trait defined by the Rust standard library that implements call. Call takes a reference to self as well as some arguments. And this code successfully verifies in kani, as you would expect. And the way the closure is actually implemented is for the data address, closures map to the closure environment, and the vtable address is a vtable that will point to this call method. The call is then replaced with the call to the data, as well as whatever arguments. However, if we change this code ever so slightly to use function once, things went wrong in previous versions of kani. So call once is the version of the call operator that consumes self. The idea is that this closure you can call one time, and then you can't call it anymore, and it's able to consume its arguments. We found, though, that this version of the call operator, in order to do that borrow-checking reasoning properly about consuming arguments, takes a by value receiver, meaning it takes a non-pointer type. And it turns out this is actually a disagreement between how the backend implements this code. So there's a difference between the borrow-checked MAR and the backend implementation. And the Rust compiler actually has a special case here where, based on the type of the vtable shim, you want to modify the function from taking self to taking a pointer to self. And we essentially had to do a similar translation in kani. So this is a case where there's an interaction between the borrow checker and what the borrow checker wants the surface language syntax to be, and how this code is actually implemented when compiling to machine code or similarly compiling to a verification backend. We have a lot more details on different trait object modeling cases in the paper. Next, I want to talk about another exciting contribution here, which is performance improvements through types. So the general challenge here is that function pointers are difficult to symbolically reason about. In CBMC, when you have a function pointer like f, the strategy to handle this in symbolic evaluation is to convert function pointers to conditional branches. So the idea is that we're going to check this function pointer f against some set of known functions, and if it matches, we'll call the corresponding function. At the end, we'll assert false to say we're going to fail if we call some function pointer that doesn't exist as a known function. The heuristic that CBMC uses is it'll consider as a possible target any function that matches the type of the function pointer. And the problem is that each of these branches must be further unrolled and analyzed and symbolically evaluated, even if that code could never actually be called. And this posed problems in practice. So we had a case study where we were trying to verify some code from the Firecracker virtualization technology at AWS. And the function we wanted to verify is this function parse that essentially takes a request for virtual memory and returns some result type. And we found that even a simple proof of this function failed to terminate within 4 hours. When we dug into this further, we found that it was the return type error, which later used a standard IO error, and that code was implicitly being dropped through a vtable call. So again, drop is sort of the destructor function, and it's implemented through this trait drop, which has a function drop that takes a reference to self and returns an integer. The problem here is that this possible function type matches on a bunch of different code in this open source project. So in particular, this call to drop had over 300 possible targets, and this was really slowing down symbolic evaluation. Our key insight was that we actually know more about the possible targets for this function call based on our knowledge of Rust MIR type system, and we can use this to narrow this path explosion. So going back to the two different cases where we use trait objects, where we're constructing the vtable and then accessing the vtable, we can think about building up a set of restricted function pointers that could actually be targets. So here I'm going to use C and T to refer to the concrete type and the trait type. And the idea is that dynamic object creation will add that potential target of the concrete objects method indexed by the trait type and the particular method on that trait. Then when we see where this vtable might actually be used, so at a vtable access, we'll add this as a call site that needs to later be restricted. And that will be keyed on the trait type and the specific method. So going to an overview of how kani works in general, we go from MIR to go to C, that C-like representation. That's then fed to CBMC, which is going to discharge to a backend stat solver for path feasibility. And the idea of applying function pointer restrictions is that we are going to aggregate across crates, looking up for every call site, what are the actual possible targets that implement that trait. We then build up a function pointer restriction map and pass this to CBMC. And CBMC has an allowance for this type of restriction because this is an optimization that verification engineers might have already been doing in C itself using manual strategy. And going back to our case study for parse, we found that this took our proof that failed to terminate within 4 hours to success in 16 minutes. So that's at least a 15 times performance improvement. And if you run this proof with a more restricted set of checks, this actually succeeds in around 4 minutes. So this is getting to times that are feasible for use in continuous integration. So finally, I want to leave you with some key takeaways. So in summary, we talked about kani, which is, to our knowledge, the first soundness-focused verification tool to cover these cases of dynamic trait objects and closures. And we really hope that other verification projects can pick up on some of the tricks or stumbling blocks that we found in this paper. Next, we talked about how we're able to use our knowledge at the MIR level to improve verification performance by restricting the set of possible function pointer targets. In the paper, we have a lot more details on things like trait subtyping and future work in that direction. We talk about our open source suite of dynamic trait object tests, like many of the examples we covered today. We talk about additional modeling edge cases, and finally, more details on our case studies. Finally, I want to encourage you to check Kani out. It's been open source throughout its development, and it welcomes contributions, and I look forward to questions in the live session. Thank you.